All right, welcome. In this explainer, we are going to do a deep dive into the fundamental principles behind the standard 12-lead ECG. We'll really unpack the physics and the geometry that let us translate the heart's complex electrical activity into those familiar waveforms we see on a tracing.
So here's our roadmap. We're going to tackle this in 5 parts. We'll start with the basics of the 12-lead system itself, then get into the nitty-gritty of how electrical signals are even recorded. From there, we'll build up to a really core concept, a 3D model called the spatial vector loop. Then see how the leads create projections of that model, and finally, we'll put it all together to get that comprehensive electrical picture.
Okay, first up, the 12-lead system. Let's take a look at what it's actually made of and how all of those different leads are categorized.
So the 12 leads are really divided into 2 main families. First, you've got the 6-limb leads, which, as the name implies, get their signals from electrodes on the arms and legs. These are broken down even further into the bipolar leads, that's I, 2, and 3, and the so-called augmented unipolar leads, AVR, AVL, and AVF. Then you have the other 6, the precordial leads, V1 through V6. These are also unipolar, and they're placed directly on the chest wall.
So how do these leads actually, record the heart's electricity? In this next section, we're going to get right into the physics of how we turn an electrical potential into those squiggly lines, the deflections we see on an ECG.
Now, a really critical concept for the bipolar leads is that they don't measure an absolute value. They measure a potential difference between 2 points. So, for instance, lead I is constantly measuring the voltage difference between the left arm and the right arm. Lead 2 is comparing the left leg to the right arm, and lead 3 is comparing the left leg to the left arm. It's all about the relative difference.
And the best way to visualize these relationships is with what's known as Einthoven's triangle. This model essentially places the heart at the center of a perfect equilateral triangle, where the sides are formed by those 3 bipolar leads. This is really the fundamental geometric framework for understanding all electrical activity in what we call the frontal plane of the body.
Okay, but the unipolar leads play by different rules. They need a different kind of reference point, and for that, we use something called the central terminal. This is a pretty clever piece of engineering. It's a reference point that's created by connecting the 3 limb leads together through resistors of equal value. What happens is, the result is a composite electrode whose potential averages out to be essentially 0 throughout the entire cardiac cycle.
So with that super stable, zero potential reference in place, a unipolar lead can now measure the absolute potential at just one single exploring electrode, whether that's on a limb or on the chest. It's just comparing that one point to a neutral background, which is exactly why we call it unipolar.
Now, there's a key technical modification needed for those unipolar limb leads. See, the native signals they record are actually pretty small, a little too small for easy clinical use. So to make them clearer, the recording system electronically augments them. This is done by disconnecting the specific limb being measured from the central terminal, which mathematically has the effect of boosting the signal amplitude by a factor of 1.5. And that is why we have the A in AVR, AVL, and AVF.
Okay, so after all of that, it really all comes down to this one single fundamental rule that governs literally all of ECG interpretation. If a wave of depolarization, that electrical force, is traveling towards a lead's positive pole, you get a positive upright deflection. If it travels away, you get a negative downward deflection. That's it. That one principle is the absolute key to understanding the shape of every single waveform in every single lead.
All right, now we get to the really beautiful theoretical core of this whole topic, the spatial vector loop. This is an incredibly powerful abstract model that helps us visualize the heart's complete depolarization sequence, but in 3 dimensions.
You have to remember, ventricular depolarization isn't like flipping a single light switch. It's a process, a wave that unfolds over about 60 to 100 milliseconds, and we can model this process as a whole series of instantaneous electrical vectors. Each one of these little arrows you see represents the net direction and the magnitude of the heart's total electrical force at one specific moment in time.
Now here's where it gets really cool. If you imagine tracing a continuous line that connects the tip of every single one of those sequential vectors, from the very beginning of depolarization all the way to its end, you generate a figure known as a vector loop. This loop represents the entire spatial and temporal journey of that depolarization wave as it moves through the ventricles. But, and this is an absolutely critical point, this vector loop isn't some flat drawing on a page. It's a true 3-dimensional, spatial loop that exists inside the chest.
A 12-lead ECG can't see this 3D shape directly. What it does instead is record 2D projections of it. You can think of them like shadows that the loop casts onto two key planes, the frontal plane and the horizontal plane. And this is exactly how the leads divide up the work. It's a perfect division of labor. The 6 limb leads are all positioned to view the projection of that vector loop onto the frontal plane, which gives us our up-down and our left-right perspective. At the same time, the 6 precordial leads are viewing the loop's projection onto the horizontal plane, giving us that absolutely crucial front-to-back and right-left perspective.
Okay, so let's put all the pieces together. In this section, we're going to connect the dots between the physical lead system that you place on a patient and this theoretical vector loop to see exactly how those final ECG waveforms are actually generated.
And here you can see that direct link between the practical and the theoretical. The very physical act of placing an electrode on a specific anatomical landmark on the chest directly determines its precise viewing angle within that 3D coordinate system. In short, where you place the lead dictates the perspective it has on the heart's electrical show. This diagram is fantastic because it shows exactly why the QRS complex looks different in each precordial lead. What you're seeing is the horizontal projection of that vector loop surrounded by the 6 precordial leads. Now, each lead sees the exact same electrical event just from its own unique vantage point. So for example, lead V1, which is over on the right, it sees the initial forces coming toward it and the later forces moving away, and that creates an RS complex. But look at lead V6, way over on the far left. It sees almost the entire depolarization wave coming right at it, which creates a tall QR complex. These different shapes aren't random. They are the direct, predictable result of the viewing angle.
Finally, let's wrap up by covering the technical standards that make ECGs a truly universal language. These standards ensure that recordings are consistent and comparable, no matter where in the world they're taken.
First up is the temporal standard, the time axis. The ECG paper speed is universally locked at 25 millimeters per second. What this calibration means is that each tiny 1 millimeter square on the horizontal axis represents exactly 0.04 seconds. This allows for incredibly precise measurement of all the intervals and durations. And second is the voltage standard. The machine has to be calibrated so that a 1 millivolt electrical signal produces a 10 millimeter deflection on the vertical axis. This standard is what allows us to accurately assess the amplitude of the waveforms, which is critical for diagnosing things like ventricular hypertrophy.
And you don't just have to take the machine's word for it. There's proof printed right on the ECG tracing itself. That's the calibration mark. It's a rectangular pulse that visually confirms the machine's settings. The first half shows the calibration for the limb leads, and the second half for the precordial leads. A 10 millimeter tall pulse confirms normal standardization, while a 5 millimeter or 20 millimeter pulse would tell you it's at half or double standard.
So we'll end with a question to really take with you. Now that we've built this entire vectorial framework, I want you to consider how a pathological change in the heart's conduction sequence, let's say a bundle branch block, would fundamentally change the shape, the orientation, and the timing of that spatial vector loop. And then, how would that newly altered loop project predictably different shapes, different morphologies onto each of the 12 leads? Answering that, well, that's the very essence of diagnostic electrocardiography.